Chapter 4 Mathematical Expectation. Mathematical expectation is another word that we use for the mean or the average of a random variable. The expected value of a random variable can be calculated depending on whether the random variable is a discrete random variable or a continuous random variable. Let's start with the definition of the expected value or the mathematical expectation. If x is a discrete random variable and px, that is the usual notation we use for a probability mass function of a discrete random variable. So if x is a discrete random variable and px is the value of its probability distribution at x, the expected value of the random variable x is given by the summation of x times px, which means you multiply each x value with its corresponding probability and add them together for all possible x's. Correspondingly, if x is a continuous random variable and fx is the value of its probability density, which means the PDF at x, then the expected value of x is calculated by integrating x times fx over the support of the x. So, in other words, you can write this as the integration of x times fx over the support of x. In these definitions, we assume that the sum or the integral exists. Otherwise, the mathematical expectation or the average is not defined. Let's start with the first example. You can see the probability mass function or PMF of x, which is the number of red cars John will meet on his way to work each morning. The possible values of x are 0, 1, 2, 3 and 4. Then you can see the probability for each of these x's. Is this a correct PMF? To check whether this is a correct PMF before we do any calculation, we have to check whether each of these px values are within 0 and 1, and we can see that it is satisfied. And then if you add these probabilities together, the summation should add up to 1, which is the total probability. And you can clearly see that if you add 0.41, 0.37, 0.16, 0.05 and 0.01, they will all add up to 1. Now let's find the average number of red cars that John will meet to his work. We start with the definition. Ex is sum of x times px. In our example, x goes from 0 up to 4. So we start multiplying x times px. For the first one, it is 0 times 0.41. Then plus 1 times corresponding probability is 0.37. Next, 2 times its corresponding probability 0.16. Then 3 times 0.05. Finally, 4 times 0.01. So if you do this summation, you will see it is 0.84, which means on average, John will meet 0.84 number of cars. Although x is a discrete random variable, the expectation can be a fraction. Next example is for a continuous random variable. The continuous random variable x is the number of errors for a given program built by a certain software company. Given that the number of errors found in is represented by the random variable x and the density function or the PDF is given here. The support of x is from 0 to 4 and it is 0 otherwise. We have to find the number of errors this company will expect to find in a given program, or the average number of errors per program. Again, we start with the definition for the continuous random variable, which is the integration over the support of x times fx dx, which is 2 times x plus 2 over 5. This is our fx, so you have to multiply this by x dx. The support of x is from 0 up to 4. Since 5 is a constant and 2 also, we can take 2 over 5 outside the integration. We will end up with x squared plus 2x dx. Now let's find the antiderivative. For x squared, it will be x to the power 3 over 3. Evaluate from 0 to 4. Then we have 2 times x squared over 2. Evaluate from 0 up to 4. Okay. Now let's simplify this. When x is evaluated from 0 to 4 to the power 3, for 0 it is 0, so for 4 to the power 3 you get 64 minus 0 over 3. This 2 will cancel out, so you'll end up with 4 to the power 2, which is 16. Okay, so this will be 3 as the common denominator. 64 plus 48 over 3. You get 112 over 3. So if you simplify this further, you'll end up with 224 at the top divided by 15. So here's the expected number of errors. If you would like, you can simplify this further and leave it with the decimal points, or you can leave the answer as a fraction. Sometimes in many problems, we are interested not only in the expected value of x, but also in the expected value of a function of x. Let's say y is a function of x and we denote it as gx. How can we find the expected value of gx? Here's the first theorem. If x is a discrete random variable and px is the PMF of x, then the expected value of gx can be given as E of gx, which is the summation of gx times px for all possible x's. You can see the difference now. When you find the expected value of x, you get sum of x times px. Now when you replace this x with gx, you do the same in the summation. So instead of x, now you have gx times px. In the same manner, if x is a continuous random variable, the expectation of gx is the integration of gx times fx. Here again, what we do is replace x with gx. Here's the example. X is a random variable given by the following probability mass function. You can see that this is a correct PMF. because if you add 1 over 6, 1 over 2 and 1 over 3, you get the total probability 1. The function of x or gx now is x squared plus 2. We have to find the expected value of gx. Okay, so let's start with the definition. Sum of gx, px. When x is negative 3, gx will be negative 3 square plus 2. You multiply this by its corresponding probability, which is 1 over 6. Okay, next one. When x is 6, you get 6 square plus 2. Then you multiply it by its corresponding probability, 1 over 2. Finally, x is 9. So gx will be 9 squared plus 2. Multiply this by its corresponding probability, 1 over 3. So this will give you 9 plus 2, which is 11, times 1 over 6, which is divided by 6. 6 square is 36 plus 2 is 38 over 2. Finally, 9 square is 81 plus 2 is 83 divided by 3. By simplifying this, you can find the answer is 48.5. This is the expected value of gx, where gx is x squared plus 2. Here's the next example when x is a continuous random variable. Fx is given, the support is from 0 to 1. We have to find the expectation of gx. Let's say our gx now is 3 times x squared. Okay, so let's find the expectation of gx. Start with the definition. Integration over the support of x, gx, fx, dx, which is integration over the support from 0 to x, 0 to 1, x from 0 to 1. Gx is 3 times x squared times the fx, 3x to the power negative 2 plus 5x dx. Okay, now let's do the integration. Let's take this 3 outside because it's the constant. Now if you multiply x squared with the other expression or with the fx, you get 3 times x squared times x to the negative 2. So the powers will cancel out. You will end up with just 3 plus 3 times 5, it's 15. X to the power 2 times x is x to the power 3 dx. Okay, so we have 3x evaluate from 0 to 1 plus 15 times x to the power 4 over 4 evaluate from 0 to 1. When x is evaluated from 0 to 1, the answer is simply 1. And for the next one, also evaluate from 0 to 1, 1 to the power 4 is still 1. So you end up with 15 over 4, which is 12 plus 15 over 4. Over 4 27, which is (71/4). The next theorem, Theorem 4.2. If A and B are constants, then the expectation of AX plus B can be written as A times EX plus B. Let's try to prove this one. Let's use the Theorem 1. According to Theorem 4.1, let's make this AX plus B as our GX. So our GX is AX plus B. Then the expected value of GX is the integration of GX fx dx. I'm doing the proof for a continuous random variable, but you can do this for a discrete case also, which will be ax plus b fx dx If we split this into two, you can get ax times fx plus b times fx dx. Okay, a is a constant. Let's take it outside. So we'll end up with x times fx dx for the first part and b times fx dx. If you look at the first one, x times fx dx, this is exactly the definition of the expected value of x. If you look at the second one, if you integrate the PDF over the support of x, it will be the total probability 1. So therefore, you get a times ex plus b times 1, which is b. So that is exactly the theorem that we have proved. Now, if we set b equals to 0, or if we set a equals to 0, let's see what will happen. If a is a constant, then the expected value of ax can be written as a times ex. So this is when b is 0. When a is 0, you get only the expectation of b, where b is a constant. The expected value of a constant is the same constant itself. So expected value of b is b. If C1, C2, C3 and up to Cn are constants, then you can find the expected value of C times Gi, which will be the summation of Ci times expectation of Gi. Okay, let's try to prove this one again. This is the third theorem. Again, if you use the theorem 4.1 or the first theorem, now our gx is ci times gix. Then the expected value of gx is the sum of gx times px. So this proof is for the discrete case with the summation, where you end up with sum for all possible x's. Gi is ci times gix times px. So the definition of the expectation of gx. So we have I going from 1 to n. We can take ci. This is for the gx. Now you see our gx is actually the sum of ci gi. Okay, so let's write the sum here. Okay, now it is correct. Our gx is sum of ci gix. So you have one summation corresponding to the I index, another summation which takes care of the values of x in our random variable. So what we are going to do is we are going to interchange these two summations, and ci is attached with the summation with I. So let's take it outside and then let's write the summation correspond to the random variable x times gix px. You see that ci is independent of x, so you can take that outside the sum of x. And if you look at this summation inside, this is exactly the expected value of gix according to the theorem 1, or according to the definition. So we get sum of I going from 1 to n ci times expected value of gix. So that is the end of the proof. Okay, let's look at the next example. Remember rolling a balanced 6-sided dice. If our random variable x is the outcome of rolling a balanced 6-sided dice, we can write the PMF of x as follows. X can have values from 1 through 6. When it is a balanced die, the total probability 1 will be distributed evenly among all possible outcomes. So all these x's will have the same probability 1 over 6. We have to find the expected value of gx, where gx is 2x squared plus 1. Okay. So the expected value of 2x squared plus 1, by using the previous theorem and corollaries, we can write this as 2 times expected value of x squared plus expected value of 1, but 1 is a constant, so this becomes 2 times ex squared. The expected value of a constant is the constant itself, which is 1. It is given that ex squared is 91 over 6, so let's use it in our equation. So we get 2 times 91 over 6 plus 1. okay, which will give you 94/3. Okay, here's another example. Now it is for a continuous random variable. You see the PDF, the support is from 0 to 1. You have to show that ex to the power r, which means you find the expectation of the rth power of x. It is better if you put this parentheses outside the r like this. Okay, so this is the expected value of x to the r. You have to show that it can be written as 2 over r plus 1 times r plus 2. And using that answer in part A, you have to answer part B to find the expected value of 2x plus 1 square. Let's make it like this. Okay. Let's start with part A. Expectation of x to the r. Using the definition, we get x to the r times fx dx. Support of x is from 0 to 1. So we get x to the power r times 2 times 1 minus x, which is our fx dx. So let's expand this expression. You get x squared times 2 times 1, which is 2, sorry, not x squared, x to the power r, minus x to the power r times 2 times x. So we get 2 times x to the power r plus 1 dx. Okay, if we get the antiderivative of these expressions, for the first one you get 2 times x to the power r plus 1 divided by r plus 1, evaluate from 0 to 1, minus 2 times x to the r plus 2 divided by r plus 2, evaluate from 0 to 1. You can see that 2 is a constant. Let's take it outside. If you evaluate x to the power r plus 1 from 0 to 1, you get simply 1 over r plus 1. And the next part, minus, again, x to the power r plus 2, evaluate from 0 to 1. Again, you get 1. At the bottom, r plus 2. Now, taking the common denominator, you get r plus 1 times r plus 2, 2 times r plus 2 minus r plus 1, r plus r and negative r cancels out, 2 minus 1 is 1, so simply this is 2 over r plus 1 times r plus 2. So you have the expression given in part A. Okay, now in part B we have to use your answer in A to evaluate the expected value of 2x plus 1 to power 2. Okay, right. Let's expand the expression within the parentheses. This is the quadratic function. So if you expand this, you get 4x squared plus 4x plus 1. You know how to expand, say x plus y to power 2, which is x squared plus 2 times xy plus y squared. So you do the same here. Your x is now 2x, your y is 1. So if you do that expansion, you get 4x squared plus 4x plus 1. So this is 4 times expected value of x squared plus 4 times expected value of x plus expected value of 1 is simply 1. Now we can easily use the answer or the expression in part A. Here you have expected value of x to the power 2, which means r is 2. So when r is 2, your answer will be 2 plus 1 times 2 plus 2, which is 3 times 4. Okay, so you get 4 times 2 over 3 times 4. Then 4 times ex, where r is now 1, you get 1 plus 1, 2, 1 plus 2, 3, which is 2 times 3. At the top you have 2 and this plus 1. Okay, so you'll get 4 over 6 plus 4 over 3 plus 1, which will be 3. Okay, so here's our part A. Here's our part B. Okay, I believe that now you have understood the expectation of a random variable, how to calculate it for both discrete and continuous cases, and also when you have a function of x, how to calculate the expectation of a function of x given it is a discrete random variable or a continuous random variable. The next section of the chapter is about moments. Let's start with the definition. Definition 4.2, the rth moment about the origin of a random variable x is denoted by mu r prime, and it is the expected value of x to the r symbolically. Again, the rth moment about the origin of a random variable x denoted by mu r prime is the expected value of x to the r. So we write it as mu r prime, which is e to the x of r. According to the definition, for a discrete case, this will be the sum of x to the r times bx. R can go from 0 up to infinity when x is discrete, or when x is continuous, this will be the integration of x to the r fx dx. When r is 0, we end up with mu 0 prime, which is expectation of x to the power 0. Any value to power 0 is 1. So according to Colorado 2 of Theorem 1, this becomes simply 1. When r is 1, mu 1 prime is the expected value of x to the power 1, which is simply expected value of x, which is the usual mean or the average of the random variable. Since this is a very useful expression in statistics, we give it a special symbol, which is simply mu, and the special name mean or the average. So the first moment about the origin. So this is the first moment about the origin of x is called the mean, where we denote it as simply mu. Okay, so mu is the expected value of a random variable x, and in view of its importance in statistics, we give it a special symbol mu and a special name mean. So here's the definition of the mean. Mu 1 prime is called the mean of the distribution of x, or simply the mean of x, and it is denoted by mu. So whenever you see the symbol mu, that means the average or the mean or the expected value of that random variable x, which is actually the first moment about the origin. The special moments we are going to define next are of importance in statistics because they serve to describe the shape of the distribution of a random variable. The definition 4.4. The rth moment about the mean of a random variable x denoted by mu r is the expected value of x minus mu to the power r, where we denote it as mu r. The expression is expected value of x minus mu to power r. We can calculate it by sum of x minus mu to power r times px for discrete case and integration over the support of x for x minus mu to power r fx dx if x is continuous. Now you can see the difference between the definition 4.3 and 4.4. In 4.3, we use the rth moment about the origin. That is the center of the random variable, the origin. But in the fourth definition, we have the moment about the mean. Now we already know what the mean is. So you find the moment about the mean. So these two are different. So you can have rth moment about the origin or rth moment about the mean. When you take rth moment about the origin, it will be simply expected value of x to the r. But when you take the rth moment about the mean, that will be the expected value of x minus mu to the power r. Okay, here's an exercise. Find mu naught and mu 1 for any random variable for which mu exists. Okay, so you have to find mu naught and mu 1, which means when r is 0 and when r is 1. Okay, let's start with the first one, when r is 0. When r is 0, you have mu naught, which is the expected value of x minus mu to power 0. So you get expected value of 1 here because any value to power 0 is 1, which is simply 1. Now, if r is 1, you get mu 1, which is the expected value of x minus mu to power 1, which is simply expected value of x minus mu. Okay, so let's use the definition using the discrete case. You can do this with the continuous random variables also with the integration. Okay, here I am using the discrete case. So this will be, now this is like a function of x. So you have x minus mu times px. Okay, so let's expand this one. So you'll get x times px from the first one minus mu times px. Okay, so let's split the summation. You get the sum of x, x times px, subtract again the sum for all x's, mu times px. So we simply distribute the summation over the two expressions. Now let's evaluate them separately. According to the definition, x times px for all possible x's for the random variable, this is the definition of the expected value of x, or simply mu according to our symbol now. Okay, so mu is a constant, right? So you can take this constant outside. So the sum of px according to the definition again, that is the total probability 1. So you get mu times 1 here. So as the final answer, you get mu minus mu, which is 0. Okay, so for the moments about the mean, when r is 0, that will be 1. When r is 1, that will be 0. Okay. The second moment about the mean is of special importance in statistics. That means when r is 2. The second moment about the origin. Because it indicates the spread or the dispersion of the distribution of the random variable. Therefore, it has given a special name and a symbol. So that is the variance of the random variable x. So here's the next definition. 4.5, the variance. So mu2, or the second moment about the mean, which can be written as the expected value of x minus mu to power 2, is called the variance of the distribution of x, or simply the variance of x, and we use the symbol sigma square, or yx or vx. The positive square root of the variance is called the standard deviation, and we usually use the symbol sigma for that. And then the third moment about the mean, which is mu3, it describes the symmetry or the skewness of a distribution. So the first moment about the mean and the second moment about the mean, they are here in our exercise. The second moment about the mean is the variance, and the third moment about the mean will give you the skewness of the random variable. Okay, here's the fourth theorem. Sigma square can be calculated using mu prime minus mu to the power 2. Okay, so what is mu prime? That is the moment about the origin. Okay, so you have to use actually the second moment about the origin here. Okay, so prime is for the moment about the origin, and this is the second moment about the mean. Okay, so this can be also denoted as the computational formula of the variance. So you can write the same thing as the expected value of x square minus expected value of x to the power 2. Okay, let's prove this one. Let's start with the left hand side, sigma square. The expression is x minus mu to power 2, which is from the definition of the variance. Variance is the second moment about the mean, which is expected value of x minus mu to power 2. Okay, so let's expand this one. Again, a quadratic form. We get x square minus 2 times x times mu plus mu square. Let's distribute the expectation. So we have expected value of x square minus 2 is a constant, mu is also a constant, it is a number, the average. So we have ex. Finally, the expected value of mu square. Okay, so we get expected value of x square minus ex is again mu, so we get negative 2 times mu, which is 2 times mu squared, plus mu square is a constant, so expected value of a constant is that constant itself, so you get mu square again. Okay, so 2 times mu square plus mu square, you get ex square minus mu square. Mu is again just the ex, so let's write this as ex square minus e of x whole thing squared, because mu is the expected value of x. Okay, so you get the computational formula for the variance. You have to be very careful where you put the square. Expected value of x square is different from expected value of x, its square. Okay, so this square is for the whole ex, but the first term square is only for x, so they are two different values. Okay, let's use this computational formula to calculate the variance of x, where x is the outcome of rolling a balanced six-sided die. Okay, now you all know what is the PMF of x. I'll write it again. Here's the PMF. We have to find the variance of x. If we use the computational formula, it is expected value of x square minus expected value of x whole thing squared. Let's start with finding ex. Ex is the mean. The definition, sum of x times px. So in this case, px is all 1 over 6. So this is easy. And this goes up to 6 times 1 over 6. Okay. Which will be 1 over 6 times 1 plus 2, 3, 4, 5 plus 6. Which will give you 7 over 2 if you simplify. Then we do the expected value of x square, which is the sum of x square px. Now you get 1 square times 1 over 6, 2 square times 1 over 6, and so on up to 6 square plus 1 over 6, which is 1 over 6 times 1 square plus 2 square up to 6 square. This will give you 91 over 6. Now we can find the variance of x, or sigma square, which will be ex square is 91 over 6 minus 7 over 2 whole thing square. So simplifying this, simple algebra, you will get 35 divided by 12, which is the variance of the random variable x. Now we see an important connection between the standard deviation or the variance. If x is the variance, then the variance of ax plus b can be written as a square times variance of x. The variance of ax plus b is a square times variance of x. Okay, here's the proof. We start with the definition of the variance, that is the second moment about the mean, or you can use the computational formula here. Since we already used the computational formula, let's go with that. Okay, so again, the computational formula is variance of x is expected value of x square minus expected value of x whole thing squared. Now our x is ax plus b, so you have ax plus b whole thing squared minus the expected value of ax plus b outside the square. Okay, so let's expand the square term. We have the expected value outside. Square in this term, we have a square x square plus 2 times abx plus b squared. So that is the first term. And then we have the expected value of ax plus b squared. Okay, let's distribute the expectation. We have a square constant coming outside, so expected value of x square plus 2ab expected value of x, then expected value of b square is a constant, so that will be simply b square, minus, let's expand this parenthesis also, so you have a times ex plus b, because expected value of b is b. Okay, next line we have a square expected value of x square plus 2abex plus b square, and now I am expanding this quadratic term. Okay, we have the negative sign outside. Square of the first term is a square ex, all things squared, first term, then plus 2 times abex plus b squared. Okay, so we have the negative sign outside. Let's rewrite this one. We get negative a square ex all things squared plus and minus another negative 2abex, this negative, so you have b squared. Now you can see that plus 2abex and minus 2abex cancel out, plus b square to minus b square cancels out. We will end up with a square times ex square minus a square times ex whole thing squared. Take a square outside, you get ex squared minus ex whole thing squared. Now you can see that this is exactly the variance of x. So that means this is a square times variance of x. So that is the proof of theorem 4.5.